So calculate the y in for these input. So y in is equal to, we know, x1 w1 plus x2 w2. So what happens? X1 is 0. These are the inputs, x1 and x2. This is x1, this is x2, and this is our w1 and w2. These are the assumptions we made. These are the given inputs. So y in is equal to x1 w1 plus x2 w2. So here for 0 0, if you calculate, it is 0. Okay, so this corresponds to 0. Next y in is, this is y in. Next, for the second case, you calculate, so 0 into 1 plus 1 into 1. So this comes out to be 1. Here it is 1. For the next case, it is 1 into 1 plus 0 into 1. So this is 1, and 1 into 1 plus 1 into 1, this is 2. Okay. So now what we have got is, assuming the weights to be 1 and 1, we have got y in using this expression 0 1 1 2. And we know that the target, if you just recall from the previous slide, so sorry, this is y. So what is the target? So the target is y, we have got 0 0 0 1. Just to compare this. So this is the y in, assuming weights to be this is the y in, this is the target, this is the target. So if you compare, it is clear that if we set the threshold value theta to be 2, okay, if we set the threshold value theta to be 2, then whenever the threshold is greater than or equal to 2, then the neuron fires, else it does not. Because see, here it is 0 1 1 and here it is 2. Okay, so now you can set the threshold, uh, uh, set the threshold, theta is equal to 2. So there is a formula for determining the threshold value. So it is very simple. Theta should be greater than or equal to nw minus p, where n is number of inputs, where n is number of inputs, where w is the excitatory weights, and p is number of inhibitory weights. So here we do not have any inhibitory weights. So it is only threshold. So n is 2. 2 into w is 1 here, excitatory. So theta should be greater than 2. Even using this formula, you can find out the threshold value, or else just by comparing the determined y in and the target y. Okay, just by comparing the determined y in and target y, you can conclude that what should be the value of threshold. So from this example, we have got the threshold value is 2. Now, so here what you can do is the output y is equal to f of y in is equal to 1 and 0 when, if y in is greater than or equal to 2, and it is 0 if y in is less than 2. Okay, so here, so what is the neural network model? It is this. So okay, so here we have x1. Okay, I'll write it just to see if I can drag. So it is not possible. Okay, so here itself I'll write, this is what we have assumed. So the weight, this w1 to be 1, this is 1, and this is x1, this is x2, and this is y, and this is y. So this is the McCullough-Pitts neuron model for the AND gate. This is the final model. Okay, this is the final McCullough-Pitts neural network model. Okay, so this is one example. Now I'll make it clear by one more example I'll take. You can take down along, it's already there in the slide. So implement the following function. Implement the following function using McCullough-Pitts neural network model. Use binary data representation for both inputs and targets. Okay, so we here we have two inputs, x1, x2, and y. So here this is 0 0, output is 0, 0 1, output is 0, 1 0, output is 1, and 1 1, output is 0. So I have simply taken a truth table how to develop the neural network model if you want to represent this particular function. So I'll tell you how to do this example. So again, first what you do is you draw a model, two input model, x1, this is x2, this is y, this is y, this is x1, this is x2. I don't know the weights. That I have to decide now. What should be the value of W1 and W2? Please note, what should be the value of W1 and W2? That we are going to determine using this particular approach. Okay. So I don't know the values of W1 and W2. So I can decide this only after doing the analysis. So how the analysis will be done, I will explain. Assume, like previous example, assume W1 and W2 is equal to 1. Let me start with 1 1. It need not be, you can take anything. Okay, all the four combinations you can take. So we know the inputs, x1, x2 inputs, and I'll write here y in, and here I'll write the y target which is given. So 0 0 0 1 1 0 1 1. Please do this and tell me what are the values of y in. Okay, y I have already know. I know from the given problem. So what is y in? You please calculate. Y in is equal to, so you know, x1 w1 plus x2 w2. So you can calculate and tell me what is the value of y in.
Ma'am, same as in last case.
Same as?
Ma'am, 0 1 1 2.
Okay. So this is your y. Okay, this is your yn. This is the first term. 0 1 1 2. Okay. Now just do the analysis. Just do the analysis. Here yn is 0, output is 0. Yn is 1, output is 0. Yn is 1, output is 1. Yn is 2, output is 0. Is it possible to set a threshold value now? So what is threshold? When you select a threshold value, it should activate and you should get the output high. So is it possible? You just compare y in and y with these assumed weights. Is it possible to set a threshold value?
No, ma'am.
No. Very good. So I'll write here, from the calculated y in, it is not possible to fire the neuron for input 1 0 only. Okay, so hence these weights w1 and w2 equal to 1. So hence these are not suitable. So these are not suitable. This is the first step. So let us go ahead. Now what I will do, I will assume a 1 plus and 1 minus. Okay, randomly I will take one W1 to be 1 is excitatory and 1 is inhibitory. I will take minus 1. Again for the different inputs, okay, I have 0, 0 input, 0, 1, 1, sorry, 0, 0, 0, 1, 1, 0, 1, 1. So I have, let me calculate Y in, you can also do it. And I have Y 0, 0, 1, 0. Just calculate Y in. Can you tell?
Ma'am, 0 minus 1, 1, 0.
Hope I am audible, right?
Yes, ma'am.
Okay. Can you please tell the value of Y in?
Ma'am, 0 minus 1, 1, 0.
Very good. 0 minus 1, 1, 0. Now what you do, you compare this. Okay, you compare 0, 0, minus 1, 0, 1, 1, 0, 0. Now if you scan the calculated Y in and Y, is it possible to fire the neuron for the input 1, 0 with a particular threshold value?
Yes, ma'am.
Yes, very good. So the threshold value will be here 1. Okay, the threshold value will be 1. So I can write here from the calculated Y in, it is possible to fire the neuron for input 1, 0 by fixing a threshold 1. Okay, threshold value theta is equal to 1. Even if you use the formula, theta should be greater than nw minus p. Please note n is number of inputs here, it is 2 into excitatory inputs 1 minus inhibitory is 1. Don't you consider only the magnitude. So 2 minus 1 is equal to 1. So theta value, even by formula or just by observation, you can it is possible to determine the value of the threshold. So once you fix the threshold value, now you can write the output. Y is equal to output Y is equal to f of Y in, which is equal to 1 or 0, 1 and 0 if Y in is greater than 1 and if Y in is greater than or equal to 1 is less than 1. So now let me go back to the model. So here I can write W1 to be equal to 1, W2 equal to minus 1. So this is how you solve any models, any functions if you are given to how to design the neural network model using this particular theory. It is very simple. Only thing is you must know the steps. Okay. Now, let me take one more important problem. I will not complete that. I will not solve it fully. I will do partially and I want you to do it. Okay. Let me just write that. Yes, take down. All of you can take down this. Implement XOR function. Implement XOR function using McCulloch's neural network model. Use binary data. It is not as simple as and or gates or because we know that when it comes to XOR, so there will be the output y will be x1 x1 x2 bar plus x1 bar x2. So this is our output. Okay. So these two conditions. So there will be, it is not just one, isn't it? We need to OR it. First we are doing AND operation, then we are doing OR operation. So if I write x1 x2 bar is, say, this is z1, and this x1 bar x2, if I write, this is z2. So my y is equal to z1 plus z2. So x1 x2 bar plus x1 bar x2. So y is equal to, if I'll call z1 plus z2, or it is equal to z1 or z2. It is equal to z1 or z2. What is z1? Z1 is equal to x1 x2 bar, and z2 is equal to x1 bar x2. Okay, that is why what I have done here is, see, apart from the input, I have two more neurons here, which we call it as this z1 and z2. Okay, that is why my model, the diagram is like this. Apart from x1 and x2, I have z1 and z2, and this will give you y, and this will give you the final output. So what I will do here is, we know that x1 x2 bar, z1 is x1 x2 bar. So here this also required. Z2 is, we need x1 bar x2. This is also required. Okay, so the model will be x1 x2 z, like this. So now what you need to do is, the steps I will tell you. First, uh, first step, okay, to implement this XOR, the first step is z1 is equal to, we know that x1 x2 bar. So this function you try to implement, x1 x2 z1. Okay, 0 0 0 1 1 0 1 1 0 0 1 0. This one you have to implement using a McCullough-Pitts neuron model, 0 0 1 0. So can you do this? So can you tell me the weights for this particular? So you can assume the weights to be
1
W1.
minus 1.
Yeah, because this we have done, just now we have done, right? Same function. Okay, you we have since we have done it, that's why I asked you. You can assume w1 is equal to w1, w21 is equal to 1. You can assume and do it. Okay, then you can assume w11 is equal to 1 and w21 is equal to -1. You can repeat the entire process if you want. So you will get finally the desired output Z1 by setting a firing this one threshold 1. You will get W11 and W21 is equal to -1. Okay. So why W11 and W21? Because it is model Z1. For the model Z1, we have the inputs 1, W11, which is coming from input 1, and W21, which is coming from the second, this one. So this is W11. I'll write here. This is W11. This is W12. This is W21. This is W22. Now this is the first step. So now second step is uh, try to get the expression for Z2. Similarly, you do it for Z2. So Z2 is equal to x1 bar x2. So you write the truth table, x1, x2 and z2. So 0 0 0 1 1 0 1 1 So here I think it will be 0, 1, 0, 0. Now you do the assume the uh, weights and you proceed. Okay, and tell me what should be the value of W21 and W22 and W21. Uh, okay, you repeat the entire process.
Ma'am, minus 1 1.
W22 should be required, and you require W12. All of you, please try to do this. Okay. So you started with the say. I'm just steps I'm telling. What is the answer you told?
Ma'am, minus 1 1.
Minus 1 1. Okay. You are telling W, which is minus 1, W12, right?
Yes, ma'am. Yes,
And
ma'am.
W22 is 1, right? Okay. Okay, you first start with just normally what we do, we assume W12 is equal to 1 is equal to, you can do W2 is equal to W22. You just calculate the Y in. I think you will get Y in is equal to 0, 1, 1, 2. So you cannot get this particular output with this value of your inputs, right? So this is not possible. Then you change the combination. So as he said, minus 1 and 1, if you do it, you will get the z in. Instead of y in, I'll tell z in here. I think you will get the z in value 0, 1, minus 1, 0. This is what I have got. Okay, so with this you just compare this particular 0 1 0 0 0 0 1 minus 1 0. So here uh, it is possible to trigger this neuron by setting a threshold value theta is equal to or greater than 1. Okay, so this is the second step. You have now got these weights. So here in this diagram, you got W11, you got W22, you got W12, you got, and W21 you got. Now what is the third step you have to do is, you have to now, third function is Y1 is equal to Z1 or Z2. So you can write here x1, x2, z1, z2, the final y. Okay, the complete diagram I'll write, but first part is not required. So, but still, since we know, I'll just write this 0, 0, 0, 1, 1, 0, 1, 1. Okay, 0, 0, 0, 1, 1, 0, 1, 1. I think it is 0, 1, 1, 0. Okay, so here you write 0, 0, 0, 1, 1, 0, 1, 1. Am I right? 0, 0, 0, 1, 1, 0, 1, 1. So this should be 0. 0, 0, 1, 0, 0, 1, 0, 0. 0, 0, 0, 1, 1, 0, 0, 0. 0, 1, 1, 0. Is this a truth table right? What I have written?
Yes, ma'am.
Okay. Okay, now what you do is, let us call the weights to be V1 and V2. Instead of avoid confusions, we will call V1 and V2. Let me go back to the diagram. Let me call this is V1, this is V2. Okay, similar steps. Okay, similar steps you repeat and tell me the value of V1 and V2. So now we know, final, I can write here y in is equal to uh, z1 v1 plus z2 v2. This is the expression. So assume both weights w1 v1 is equal to v2 is equal to 1. Okay, you calculate y in. I hope you are following what I am doing, right?
Yes, ma'am.
Okay, okay, fine. Yeah, now I think y in, if you calculate, you will definitely you will get because of the input combinations. I think it is 0 1 1 0, right?
Yes, ma'am.
Yes. So with this, what we can conclude is we can set a threshold value theta. Obvious, it should be equal to or greater than 1. So v1 is equal to v2 is equal to 1. Now finally, for the XOR function, using this MP neuron model, we can write that w11 is equal to w22 is equal to 1, w12 is equal to w21 is equal to -1, v1 is equal to v2 is equal to 1, and the final model will be output y is equal to function of y in is equal to 1 or 0 if y in is greater than or equal to 1, and if y in is less than 1. This is for the last. Okay, so here let me come back to the model. So I will write here the value of w1 w2, this is equal to 1, this is equal to 1. So w11 is equal to 1, w2 is equal to 1, this is equal to -1, this is equal to -1. Okay, say you just assume that you don't know XOR function, you don't know what XOR is, but say you know the truth table here. When you have the truth table of any function, any logic circuit, any you have studied in your digital systems a lot of digital circuits, so all the circuits we can implement it using basic gates. Okay, or even the universal gate. So if you know the function, you can definitely implement those functions using neural network models. So out of many network models, we have discussed a basic one. Okay, so McCullough-Pitts neural network model can be used to implement this. Okay. Yeah, now one more concept. Just 1 second. Yeah, one more concept. It is called linear separability. What is this linear separability? It is the separation of the input space into regions based on whether the network response is positive or negative. Let me be very brief. Okay, I'll just try to give you the concept. Just see here. Uh, say this here we have positive response, here we have minus, here we have minus, here we have minus. So this may be a simple what you call the representation of in all the four quadrants of a and function. So we know that for and function we say 0 0 0 1 1 0 1 1. So 0 0 0 1, this is for and function using binary input. Say instead of binary input, if we take bipolar input, so bipolar means it is 1 to -1. See, binary is 0 to 1. Okay. Bipolar is it is -1 to +1. So here what you do, you replace the zeros by -1 and you write the output. So what happens? It is -1 will be -1. -1 plus 1 will be -1. 1 minus 1 will be -1, 1 and 1 will be 1. So this one you try to plot it in four quadrants. When you plot, you will get something like whatever I showed in a yellow mark. So now what this linear separability tells is, so you can, if you can draw a line which can separate this, okay, okay, then the decision line which is drawn separating the positive response region from the negative response region. So by making use of this particular line, we can calculate the whether we can decide the weights of a neural network model. This is what this linear separability tells. When we solve a problem, you will understand it better. Okay. So I'll solve one problem later and I'll make the concepts very clear. Now next comes a hub network. You might have heard this is a very famous network in neural networks. So it was developed or stated by Hebb, Donald Hebb in 1949, that in the brain the learning is performed by the change in the synaptic gap. Okay, a small change. Okay, so here same concept if you bring it to artificial neural network. So the weight vector is found to increase proportionately to the product of the input and the learning signal. Okay, so here the learning signal is equal to neurons output. Like this, if I just tell you in one or two sentences, this is the hub network, you will not understand. We'll solve one problem and I'll make it clear. Okay, but please note that whenever you solve or whenever you use make use of hub network, you have to two expressions you have to write clearly. One is the weight update. Weight update in Hebb rule is wi new is equal to wi old plus xi y. Okay, so where I is, you know, that the number of inputs depending upon that. So bias update, the bias new is equal to bias old plus y. So whatever the old bias value we have plus y. Okay, what is that y? I will tell you. Similarly, the new weight is the old weight plus xi into y. Okay. So normally we use Hebb's rule for bipolar data only. For binary data, it may not give accurate answers under two conditions. Okay. That's why we use bipolar data. And here, if you compare, this xy is the change in weight. This is very important. This is that weight which makes the new which gives you the new weight. So change in weight is w delta w is equal to xy. Again, as I told, no, all this theory, if I tell, you may not understand. We will solve one problem now. Okay, and it will definitely, it will clear your doubts. So what I have taken here, the problem is use design hub network. Okay, design hub network to implement OR function. So you let us consider OR function. Consider bipolar inputs and targets. So here in this application for this particular implementation, we are considering bipolar inputs only. Okay, to implement OR function. Second. Okay, this I will do later. OR function. So I'll do just now. I'll do AND function. Then I will do OR because I have solved AND here, and OR I can give you homework. Okay. Okay. I'll write for next 2 minutes. I'll just write whatever is required. You can just take down. Okay. I'll not explain. Okay, so I hope you would have taken down this. This is the input, this is the target. So here, please note that I have considered bipolar inputs and targets. So bipolar means it is -1 to +1. So wherever 0 is there, it is replaced by -1, and accordingly I have written the targets. Okay. So the bias value here I have assumed it to be 1. Okay. Uh, okay. What is the procedure? I will tell you. So what I will do is initialize. First part is initialization. So the first part is initialization. You assume initially W1 plus equal to W2 equal to B equal to 0. Okay. This is initialize. The first step. Normally we initialize it with 0. Now next step is, okay, the first step in the truth table you consider. First input, that is x1 x2 b. Okay, x1 x2 b. Okay, that is equal to 1 1 1. x1 x2 b is equal to 1 1 1. So for that we know that target is equal to 1 from the previous. Yeah, that means target is equal to 1. It is nothing but the output y is equal to 1. Now make use of the weight updation formula. So what it is, wi new is equal to wi old plus xi y. So wi new I have to calculate. My wi old is 0 plus x, here x1, the first input I am considering. So x1y. So here x1 is 1, y is 1. So this is equal to which is nothing but 0 plus 1 into 1. Okay, 1 into 1. So which is nothing but 1. So what is wi new now? W1 new is 1. Similarly, you calculate W2 new. Similarly, calculate W2 new. Again, W2 old. Okay, so that is 0. W2 new is equal to W2 old plus X2 into Y. Okay, X2 is 1, Y is 1. Okay, so X2Y, which is nothing but 0 plus 1 into 1, which is nothing but 1. So W2 new is 1. Now you calculate the bias updation. B new is equal to, what is the expression? B new is B old plus Y. B new is B old plus Y. So it is B old plus Y. B old is, we have assumed it to be 0. Y is 1. So this is equal to 0 plus 1. So it is 1. Our B new is 1. So we have got W1 new, W2 new and B new. So what is the next step? Okay. So now what I have got, I'll just take from my previous slide, W1 new, W2 new and B new. All these are 1. Okay. Now, as I have told, the change in the weight wi is okay. The weight change is normally xy into y. This is called weight change. This is not required because we have got it from previous 0 0 0 to it has become 1 1 1, right? So here we can just write w delta w1 is x1y, which is equal to 1. So delta W2 is equal to X2Y, which is equal to 1, and delta B is equal to Y is equal to 1. This is just for your understanding. I told what is the weight change here. Now you repeat the entire process. You have to repeat for second input. Okay, this takes time. This takes lot of time. Second input x1 x2 b, which is equal to 1 minus 1 1. Correct, no? Second input 1 minus 1 1, and y is uh, and y is 1. Y is minus 1. Okay. Now what you have to do is, now old w1 w1 w2 b old is, please note, this is equal to 1 1 1. Okay, w1 w2 b is equal to 1 1 1. Now you have to make use of this, and you have to, for the second iteration, you have to calculate the new value of w1 w1 new, W2 new, and B new. You calculate and tell me what are these values for the second iterations. Here, I repeat, you have to make use of W1, W2, B old is 1, 1, 1, and Y is minus 1. See, Y is minus 1. W1, W2, B old is 1, 1, 1. Okay. You have to make use of this, and your inputs X1, X2, B is 1 minus 1. So make use of the formula. Okay, make use of the formula and tell me the values of new W1, W2 and B. If you tell fast, I'll leave you people early. Similarly, you have to do it for third iteration. That means for third input. That is your x minus 1, 1, 1, y is minus 1. Similarly, you have to do it for fourth input. Minus 1, minus 1, 1, y is minus 1. Tell me the values of new weights. Yes.
W1 new for the second iteration will be 0.
Okay. Wait, what I have got? Yeah, 0. Correct. This is 0. Very good.
B
0.
new will be 0, and W2 new for the first iteration will be minus 1, and for the second iteration, no, for the first iteration it will be 1, and
Now,
the second iteration.
first iteration is we have got, right. This is the what we have got now. This we have got, right, for 1 1 1. Previous slide we have got, right? 1 1. So second input for this, what is the new second input? This one you tell. 0.
0.
This is also 0.
Ma'am, I got 2.
Huh? This is not 0.
Ma'am,
Yes, Malaika, I could not hear your voice. Any
ma'am,
other answer?
is it 2?
Anupama? Is
Yes,
it?
ma'am, is it 2?
Yeah, it is 2. Correct. This is 2. Please check. This is 2. And this is B new
0, ma'am.
0. Please check W2 old plus X2 into Y. This will be 2. Please check. If you are not got, you tell me. Similarly, for
Yes,
the,
ma'am. 2.
are you getting?
Yes, ma'am.
Okay, fine. Yeah, because here chances are there that you will do some mistakes. Okay, you have to be careful with the plus minus and all. Okay, so now can you just tell me the values for the third iteration? W1, W2, and B new. Similarly, for the fourth inputs. Yes, anybody?
Ma'am, is it 1, 1 minus 1?
1, 1 minus 1. Very good. Yes, this is 1, 1 minus 1. Now tell me for the last fourth input, what are the new weights and bias?
Ma'am, is it 2 to 0?
It is 2 to 0. No, 2 to minus 2 I have got. Just check. I have
Yeah,
got.
2 to minus 2, 2 to minus 2.
Yeah, 2 minus 2 I have got. Okay, I hope all of you could do this. Okay, this is very, very important. You have calculated for all the four input sets the updated weights and biases. After this, now we have one more step. Okay, one last step. That is again, it takes lot of time. I'll just tell you what we can do now. Uh, so here I'll just write for your understanding inputs, then yeah, x1, x2, b, then I have y, then here, okay, then I have here weights I'll write. Okay, so here we have 1 1 1 1 minus 1 1 minus 1 1 1 minus 1 minus 1 1. The y is we, okay, y is, we know that it is all 1 minus 1 minus 1 minus 1. Okay, so now here weights what we have got is I'll write w1 w2 b. I have got 1 1 1 0 to 0, 1 1 1 0 2 0, 1 1 minus 1 2 2 minus 2. Okay, 1 1 1 1 minus 1 2 2 minus 2. This is what I have got. Very, very important step. Okay, this getting this table is very, very important. So now last step is we have to make use of the linear separability concept, and we have to draw the four graphs. Very simple. Just keep in your mind. Uh, Bias, normally the separating line equation is the bias plus x1 w1 plus x2 w2 is equal to 0. So the equation for the line x2 will be minus w1 x1 by w2 minus w1 x1 by minus b by w2, provided w2 is not equal to 0. Okay, provided w2 is not equal to 0. So in all these cases, the value of w2 is not 0. W2 is not 0. So we are making use of this separating line equation. You may ask me how I got this separating line equation. We can derive this making use of that x1 plus x2 w2 plus b equal to the condition we have to apply and do the derivation. That is not required. So directly I am giving you the separating line equation. From this I have written x is equal to something plus something, or in this case it is minus w1 x1 by w2 minus b by w2, provided w2 is not equal to 0. Now what I have to do is uh, so for here just refer this particular table and write equation, 4 equations you have to write now. So first equation x2 is equal to, make use of the first row, w1 1, w1 x1 by w2 is 1. Okay, so minus x1 minus it should be in terms of x1. So minus so I'll write here, 1 second. So the first equation will be x2 is equal to minus w1 by w2 into x1 minus b is 1 divided by w2 1. So this will be minus x1 minus 1. The first equation, x2 equal to minus x1 minus 1. Okay, similarly write the second equation. Second equation will be, again here what happens is minus 0 x1 by 2 something 0, next 0 by something. So this second equation is x2 equal to 0. Third equation is equal to minus 1 by 1 minus 1 by 1 x1 plus 1 by plus 1 by 1 it will be. So it will be x2 is equal to, if I am fast please tell me, I'll slow down, I'll explain again. Okay, this is important. X1 plus 1. Fourth equation then will be minus 2 into x1 by 2 plus, because minus of minus will be plus, so plus 2 by 2. So again fourth equation also will be same, x2 is equal to minus x1 plus 1. So 4 equations you have got. Anybody any doubts how I got the equation for 4 equations using this particular expression? Is it clear?
Yes, ma'am.
Okay.
Yes.
Okay, fine. So 4 equations you have got. Now what I will do is, I'll draw the 4 graphs. Okay, so plot the graphs. See here. So this is first graph. This is my second graph. This is my third graph. So here only 3 graphs because last 2 equations are same. So this is my x1, this is my x2. This is my x1, this is my x2, this is x1. Okay, this is x2. So you plot all the graphs. So here I will just mark, because we know that when this is a what I started with AND gate. So here if you just see the first inputs, for first quadrant all positive, then we have uh, uh, you can just see here. So 1 1 it is 1, then for all the other 1 minus 1 minus 1 1 minus 1 1 it is negative. So directly I make use of this concept here. So here I just mark, this is plus, this is minus, this is minus, right? Minus, this is minus. Okay, so same thing, plus, minus, minus, minus. So plus, minus, minus, minus. So now you plot those lines you have got now here. First one is x2 is equal to minus x1 minus 1. x2 is equal to minus x1 minus 1. It will come somewhere, if you try, I just see, you give the values of x1, get the values of x2, something like this it will come. This is the equation for the x2. Second one is x2 is equal to 0. x2 is equal to 0. So it will come somewhere here, right? x2 is equal to 0. So I don't have to mark anything. Okay. So here this is x2 is equal to minus x1. x2 is equal to minus x1 minus 1. x2 is equal to 0. Third one is, what is that line? Third and fourth, x2 is equal to minus x1 plus 1. Minus x1 plus 1 means somewhere here it will come, right? It will come somewhere here. Correct? x2 is equal to, okay, now very simple. Okay, after we plot the lines, the concept of linear separability, what it tells is which line, okay, which line separates the positive response with the negative response. Which line? Now out of these three, which line separates positive outputs with the negative? Anybody?
The third graph.
Third graph, very good, excellent. Okay, so third graph separates. So this is first graph, this is second. So for the third and fourth case, we have got this. See here, this particular line minus x1 plus 1, it separates the first, say positive is here, all negatives are here. Whereas here it is not so. Here also we could not separate it. So third but the this one, it gives you the condition. Okay, so yeah, first, yeah, it gives you the condition. Why? Just to see here, just for your analysis, this 1 1 minus 1 2 2 minus 2, these weights, it is almost the same. See here, this is just doubled, right? That is why you have got the same what graph. Okay, so now with this what we can conclude is, we can, the last case or the third case, we can consider, and we can assign the same weights to our neural network model. So in this case I will write w1 is equal to 2, w2 is equal to 2, and b is equal to minus 2. I'll consider the last case, and I just write that this is the neural network model or HebNet for the AND function. Okay, so let me just go back to where I have started. So here I have started. So the model will be, it will be, I'll just write y, okay, y, this is y. So here like this comes, this is x1, this is x2, this is my bias. So bias is -2, this is 2, this is 2, this is my x2, this is my x1, and this is my bias 1. Okay, this is my bias 1, this is x1, this is x2, and these are my weights. I have just written -2, the last case I have considered, and this is my final output. So this is the HEBnet to implement AND function considering bipolar inputs and targets. So now I'll give you a homework. Just do it for OR function. Considering bipolar inputs and target, you do the entire process for OR function and try to develop the Hebb network. I'll just take attendance once. Any doubts? Anybody?
No, ma'am.
Is it clear? Any doubts? Any confusions? Anything you want to ask? I don't know. I sometimes I feel I don't get responses from you. Only 2 3 students are just giving are responding. Maybe is it the same in all classes? I don't know. But please try to solve by yourself. Okay. Uh, it will be difficult. If you don't understand in the class, it is difficult to get from the textbooks. So I request you to be attentive in the class. Okay, you solve the problem along with me. I think I am not that fast. Slowly I am doing. Okay, so okay, that's all for today. Let us close. Thank you.